handsome guy. You're a bit of a, I don't know, kind of a Clint Eastwood thing going on there. Hey, Mike?
I mean, oh yeah, that is me.
You know, I feel like you'd look perfectly at home there with like a 6-shooter on your belt or something.
I was thinking of getting one of those there for guys who don't listen when I'm talking.
Well, where did you get that belt buckle? That's pretty manly.
That's an antique. That thing is 35 years old. Was made by a young entomologist in Montana. Was the state entomologist. That was his first cougar belt that he built. So it's a piece of artwork. Maybe one day it'll be worth something actually. But it's my signature belt.
Oh, that's a great story. When you wear it well, you're a handsome fella, as well as being quite intelligent. I guess, I don't know, I'm not the kind of guy to do really formal introductions in terms of all of your education and your different vocations, but what I would say about Mike, and what I find really interesting about Mike, is that Mike has had a lot of different intellectual pursuits and passions, and from the time that I first got to know him, we talked a lot about different things like the stock market, insects, and different agronomic stuff, but he's always learning, and he's one of the more interesting scientific guys you'd run into. And I'm really interested to hear about his latest passion, which really aligns well with what we're marketing. It's sulfur. So with that, Mike, I would let you take over. Just ask you to make sure to get in that mic good. We're going to record this. Hopefully you can share it on social media and share it on YouTube. A little bit of your knowledge. Help us out with the best audio quality you can, and you can take it away from here, and I'll move the slides for you as you request, okay?
Okay, thanks a lot, Dan. For you guys that don't know me, I was the entomologist with Alberta for a number of years, but since I retired and joined Agrotrend, I've sort of broadened my horizons into a lot of physiology that's going on in plants, because nobody really talks about it in a big way. So, and I even spell sulfur the Canadian way rather than the American way. So nowadays I spend all my time sitting here in my office in the basement by my computer-linked microscope, taking a look at what's going on in plants. And I spend a lot of my time looking at the research that's been done. And Elston has been our lead guy for years on sulfur, did his master's on it way back when. And I had absolutely no interest in nutrients up until about 10 years ago. So I've tried to learn as much as I can by reading largely, because I wasn't really a fertilizer salesman or anything in my life. So I spend most of my time looking at the actual role of these nutrients in plants and the interactions in them, and let the agronomist deal with, how much nutrients you need in order to grow a crop. So let's go on to the first slide, Dan. Oops, where's the other one? The one I sent you, the last one. Yes.
Yeah, I didn't realize you wanted this at the front. I apologize. Just one moment.
Okay.
Yeah, I'll put this
will
in.
Catch everybody's attention. Yeah.
Oh, well, yeah, everybody's sleeping at this point, but now they're awake. So that's
No, they're not going to sleep. For you guys that are listening that haven't heard me, and even if you heard me in Regina this summer, I'm going to be covering a few things here that if you really are paying attention, will forever change the way you look at plants, and maybe help you understand how plants operate. But this was in a review of sulfur that was done early in 2017. This really popped out at me no later than yesterday, and this is really amazing. Optimizing the S nutritional status of a plant is equivalent to enhancing the capability of a plant to cope with stress. And that means drought stress, heat stress, sun stress. All the stresses that plants face are what reduce eventually their productivity. Now, sulfur is mobile in the soil. It's not as mobile in the plant, but the stuff I'm reading now is going to show that the soil guys were wrong for a long time about sulfur mobility in plants. And now the recent research, which really is at much higher levels of understanding in the plant than ever before, is conclusively showing that virtually all nutrients have some mobility. Maybe manganese is the one, and maybe a little bit of calcium. but that's irrelevant. You had here an ability to supply, which is rare, a plant and nutrient that it needs all the time through the rooting zone because sulfate is mobile in the soil. So if you're going to put this on, and a lot of parts of the country are dry, we got a decent crop last year in lots of Western Canada because of reserved moisture from the year before. If you guys haven't had fall moisture, that soil profile might be fairly dry by now. So you're going to want to get this on before we get a lot of moisture moving down in that soil profile in spring to move some of that sulfur, even if it's a small amount further down in the rooting zone. You have to expect some rain, which is going to allow the plant to access the nutrient throughout the growing season. And for me, that's the big issue with many of the immobile nutrients like the phosphorus and the potassium. We can't move that stuff down very easily. So let's go through this, and I want to spend some time, just probably about 20 minutes, 15, 20 minutes, to go through this presentation and take a look at some questions, and you can send them to Dan. Next one, Dan. So we're looking at growing this crop, and early in the season, we don't have a lot of need, but it ramps up really fast, and this big curve up is really when we're going to be sucking a lot of nutrients, and that's the time when that sulfur is going to be picked up in a huge way up until flowering, and then it sort of levels off. And that plant is loading up with all the nutrients during that, and it's also supporting, amazingly, the reproductive parts. And one of my presentations at Farm this year is going to be talking to everybody about the fact that we talk about the reproductive time in the plant when pollination takes place. My point is that those reproductive organs in wheat start below ground, and then the head comes up way back here just after tillering. We are supporting the growth of not just the vegetative part, but also the reproductive organs totally through that growth phase. And it's through that growth phase that I think we missed the boat by loading the plant up with all the micro and macronutrients. And sulfur is involved in all of those phases because it's involved in the production of proteins. I think Elton probably covered this, that really, we'll look at it in a minute, the production of proteins is key to all these plants. So you have a product here that will supply this plant without doing anything throughout its growing season totally, where things like phosphorus and potassium can become restrictive. The micronutrients can be restrictive. So you're the only product that handles that, and sulfur is the first responder to stress. Next one. Next slide, Dan. Now take a look at this. This is canola. The yellow line is the canola uptake, and it sort of guides you to that reproductive point. Look at the massive amount of sulfur that canola takes up relative to spring wheat, peas, and lentils. They all need it. Anything that produces proteins in a big way and just for plant function needs sulfur. But canola is a big one. Next one. So why are we have a problem with shortage of sulfur? Take a look at this. This was a study done in southern Alberta, and it was just a bunch of soil samples taken across the field at regular intervals. We have variability like crazy with sulfur, from a minimum of 22 to maximum of 900. And Nelson's always talked about this. We have massive variability. So in some parts of your field, you can have lots of sulfur and the plant is fine, others not. Biosalt strikes me as giving you a uniform supply of sulfur to all plants across that field with virtually no downside that I can see in terms of the possibility of oversupply. And with canola, that would be really, really important throughout its growing stage, more so than other plants, in my opinion, because canola's demand for sulfur, because of a lot of the sulfur compounds in the plant, is massive. Next one, Dan. Oh, that's slipped in there somehow.
Yeah, right here, sorry.
Now, That's the one. I throw this in because this may explain, there's two reasons why we talk about sulfur even in shortage. Number one is we've cleaned up our bare stacks of sulfur dioxide and sulfur emissions. And that's happened all through the developed part of the world, including Europe. And Europe is facing the same issue with deficiencies of sulfur. And most countries are now because the atmosphere isn't supplying it. And if you take a look at this canola production, it kind of explains to me why we are running out of sulfur. Look at the acreage increase from, say, 87 to 215. We have tripled our canola acreage, but more importantly, we've doubled our yields. So between those two on a wheat canola rotation on the prairies, we have sucked out more sulfur than probably all the canola production prior to probably the early 1880s or 1980s in this part of Western Canada. So it's not surprising that sulfur is showing up as a deterrent to productivity and stress management in plants. Next one.
Well, and if you charted this on a graph, Mike, what would that look like in terms of where we're going? I mean, part of our argument is you're going to need to get more on for what's coming.
For sure. You know, we got a Canola 100 contest, and we're ramping up canola production simply because the genetics is improving. We're getting having a better understanding on how to grow this. We're getting things like sclerotinia resistant varieties that are coming along, clubroot resistant varieties that are now being developed. So in fact, once we manage these diseases a little better, we will have a massive increase in our productivity and the demand will continue to increase. And the one thing that is amazing is that, I'll get ahead of myself here. When we talk about the disease situation, I'll cover that. But sulfur is important, really important, and starting to show data on sclerotinia that sulfur is really key to plant response to sclerotinia invasion. And in fact, plant disease is typically referred to as sulfur-induced resistance. So I'll cover that in a second. So if we look at this, we're 20 million acres. We had 21.7 million acres. Who knows where we're going? If lentils go in the toilet, you know, we could be looking at 21, 22 million. I'm not following the prices of canola, but, you know, in Western Canada, canola has been our savior in terms of our rotations. We have very few crops we can grow on this kind of acreage other than wheat and canola. So I would expect that canola acreages are going to stay up, and the sucker of sulfur out of our soil is going to increase over time as yields continue to rise. Now, I throw this in here because I've seen this thing my whole life here sitting at meetings since I joined Alberta Agriculture, and I noticed one thing that hardly anybody has noticed. It strikes me, maybe other than Nelson. If you look at Mulder's chart, what do you notice? Sulfur isn't on it.
Yeah.
Go figure.
Where's biosul?
Go figure. What this means to you folks is that sulfur does not interfere or is related to other nutrients in a significant way, both negatively or positively to a degree. It's positively related in that sulfur enhances nitrogen uptake, plant physiology, but it doesn't interfere with the uptake of other nutrients or deter it other than for molybdenum. There are some indications that high levels of sulfur will interfere with the uptake of molybdenum because the transporters in the root system for sulfur and molybdenum may be the same, or at least some of them may be the same. So, and Elston can comment later, but I don't think there's any way that biosul can be have a negative impact on the uptake of other nutrients. So that is kind of pretty surprising for me, and why I got excited about how it helps plants deal with stress, and I'll get to that in a minute. Next one, Dan. Now here's what it does, and you know, sometimes I get really complicated, but just sort of grab this point. there are several different classifications of groups of compounds and nutrients that are used by plants, and one of them has these two lumped together is different from all the other ones because these are the two that are involved in the making of amino acids. So they're grouped together. And when you look at symptoms, chlorosis becomes the symptoms largely. But the key thing here is that the ratio between nitrogen and sulfur has to be managed, because if you have too much nitrogen and not enough sulfur, you don't get productivity. You got too much sulfur, not enough nitrogen, you lose productivity. It's the balance of those two. That's why Elkin talks about the N/S ratio. Those are key things. And most guys know their nitrogen and have no problem putting on the nitrogen. But if you put on the nitrogen without the sulfur, you got a problem. Your productivity goes down. And I was at a meeting in Calgary last week, I was telling Dan, and one of the guys said, since we've applied sulfur, we're finding that our nitrogen use efficiency is going way up, and I'm producing a bushel of wheat as a pound of nitrogen as far as I can tell in terms of my application. So they're puzzled by it. And I said, well, I'm not so puzzled because sulfur has some ability to make nitrogen much more efficient. And plants will do whatever they have to do to get nitrogen. Because nitrogen is the big molecule that is used for building the plant. Sulfur is the big molecule for building the plant. That's why they're grouped together in terms of the importance of proteins. And you can look under sulfur there in components of cysteine, methionine, coenzyme A, and I want to talk specifically about glutathione here in a second. Because when you look at how the sulfur is incorporated into the plant, glutathione becomes really, really important, and not many people, if any, talk about that. But that's sort of a technical thing. Nitrogen and sulfur are tied at the hip, no two ways about it. Next one. Just throw this in quickly. The other thing that I gave as an explanation on why the sulfur is really helping in terms of making things efficient is if you look at this thing word here, ferredoxin. And when you see ferro, that means iron. Sulfur is involved in linking a lot of iron molecules and a lot of other molecules in the plant. So besides its protein capabilities, it's involved in linking through what are called disulfide bonds, other atoms together to make molecules within the plant. And ferredoxin is what is really important in terms of photosynthesis and a whole bunch of reduction operations in the plant, and makes all kinds of sulfolipids, vitamins, and glutathione is there at the bottom again. So you don't need to sort of worry about that, but it is involved in a whole lot of functions within the plant. Next one. You take a look at this one. This is ferredoxin. You can see these sulfur molecule atoms here are key in terms of binding things together within the plant. So when you're short of sulfur, molecules and all kinds of other products within the plant have difficulty being produced easily. When a plant has to struggle to access nutrients through its roots largely, something has to give. Next one. This is nitrogenase. Key in terms of nitrogen fixing in plants. And you take a look here, you can see the MO is molybdenum. And then you can look at all these sulfur and iron bonds that occur in what are called MOCO, molybdenum cofactors. Molybdenum never works by itself. So this is, to me, part of the reason why when we have plenty of sulfur, the plant could be much more efficient, not just with nitrogen, but the linking of a whole bunch of other elements and micronutrients within the plant to make all these molecules to function properly. It's involved in activation and support of a whole bunch of molecules. Next one. And this is the key one. Within a plant, when it comes under stress, it typically produces what are called reactive oxygen species. You can see it. Dan, can you use I'm using my cursor as though you can see it, but I don't think you can. Can you use your cursor there to show the reactive oxygen right there? See, and it's produced by a whole bunch of stresses that occur in the plant, and it gives out an oxidative burst. And the oxidative burst has both got positive and negative aspects. It's like, what do we get in human beings when we get the stress and oxygen molecules that are causing cell damage? Free radicals. That's what a reactive oxygen species is, and they cause a lot of cell damage. Now, nobody much talks about it, but if you read the current literature in plant physiology, this is where a lot of the action is, all about managing this reactive oxygen species here. And things like copper and iron, if there's too much of it, are actually negatively impacts on the plant. And the plant has a whole bunch of ways to deal with managing these throughout the plant to protect the plant from these nutrients. But reactive oxygen species cause a lot of damage. And the first responder to reactive oxygen species under stress is glutathione, that sulfur compound that I talked about, along with a whole bunch of other things called sods. Next one. I just threw this in because it's pretty important. This is the nutrient content in a wheat seed. And one of the things, we always talk about canola and sulfur, but take a look at this. This one in the endodermis, which is really what feeds the emerging radical in coleoptile, or the emerging seedling. 50% of the sulfur is in the endosperm, and the remainder is in the seed coat. There's nothing more important in that endosperm or higher volume than sulfur, other than nitrogen, which isn't included here. So sulfur is really key in the seed itself. And that's why the plants, and virtually all plants, when they're maturing seed, move nutrients from the old leaves and finally from the stem into the seed. So I think over time we're going to find out that sulfur applied throughout the growing season and late, and the availability late, which is what biosul provides, is going to give us a whole lot better seed quality and probably better germination come springtime. That was just a sideline. So sulfur is important everywhere. Next one.
Yeah, I know that we had supper with Neil Weens last night, and he mentioned that they're seeing a higher protein in wheat often.
For sure. And that's what you would expect. You would expect is a higher protein, and that's what the guys in southern Alberta said as well. We're getting bigger yields and higher proteins, and they can't figure it out other than those fields with the sulfur seem to be leading that pack and that change. So lastly for me is really getting complicated, but we'll make it as simple as we can. The question is going to be for you guys to understand is how does the plant get the sulfur, and how does the plant actually get all the nutrients? Well, this is a little fuzzy, but this is cells. Each one of these little squares here, if you look at them, that are clear, are cells. And plants are made up of billions and billions of cells. And it's all about the activity of the cells that is related to how the plant takes up the nutrient. And mostly cells in the root system, because of course plants get their nutrients largely through the roots. So I'm going to spend a few minutes talking about how plants pick up nutrients, and this does not apply to only sulfur. Before I start into this, we now know that the plant has the ability to do things in response to what it's perceiving in the rooting zone and in the upper atmosphere through the shoot. And the plant changes its genetics, or it upregulates genes to help it secure the nutrients that are hard to get. And that's all of them depending on the environmental conditions. And they do that by producing transporter proteins in the root hairs and the root tip so that they can extract the nutrients that the plant, as it monitors it, excuse me a minute, as it monitors everything that's going on, makes those changes. And we'll talk about that for a second, because I think it's the key for farmers to understand that this plant knows what to do and does this automatically. Next one. Here's a cell. And within this cell, you can see a couple things. And Jeepers Creepers, Dan, can you get your pointer out there again? You got this big thing called the vacuole here. When a plant takes up nutrients that it doesn't use right away, it stores it in the vacuole, and the materials can be toxic. It'll store heavy metals and so on in there, and this vacuole can expand to fill up almost the entire cell. The other part of this cell is the plasma membrane, Dan, and that's that blue line just around the edge of the cell, the total cell.
Right here?
At the top, that blue line. And that, I'll show you a close-up of that, is key, as well as the big nucleus at the top. Okay? Next slide. Okay, so that plasma membrane, that blue line around the cell, and every cell is covered by it. This is a close-up of what that looks like. And you see on the right side, you can see this, what looks like a ladder with blue dots. Those blue dots are all phosphorus. Every cell is surrounded in the plasma membrane by phosphorus. That's why P is key. Nitrogen and phosphorus are key to building the plant because the cells all have it. The phosphorus also is used for building all the DNA and ATP. Now, if you take a look at this membrane, it's a bilayer, 2 layers. You can see there's bilayers, and it's a phospholipid. So it's impermeable to most things other than ethanol and water. Glucose, fructose, it's impermeable as you go down. All the cations and anions, it's impermeable to, and amino acids and ATP. So what that tells you is that every cell is impermeable to the random passing of nutrients and molecules through it. And what the plant does is it puts in transporters into those plasma membrane, and it changes the transporters depending on the nutrient availability and the level of nutrients that it's exposed to. Next one. So here's another look at it. You can see the blue or the phosphorus. So the plant puts all of these transporters through that plasma membrane, and they've got little antennae that they measure what's going on. They actually measure the level of sulfur, but not at sulfur. They measure glutathione, they measure cysteine, the compounds that are producing. So they're measuring all that all the time, and they're releasing, or they're allowing entry into the cell. And if there's too much, they move that comes into the cell into that vacuole. And the vacuole itself also has transporters in it that controls what goes in and then releases it out to the plant as the plant uses it. Next slide. And there's a whole bunch of transporters. There's high affinity transporters, low affinity transporters. There's transporters in their leaves. There's transporters in the vacuoles. And these transporters are controlling everything, and the genes change the level of various transporters in each cell to make the plant work and to balance the nutrients that are there. The harder the plant has to work to get nutrients into the system, the more energy it takes and the more the plant moves its photosynthase from the leaves to the roots, because the roots can't feed themselves. Next slide. And this is just to show you, this center part is the vacuole. The outer orange ring is the plasma membrane. And you can see that within the vacuole, there are all of these transporters that are moving things in and out as the cell needs it. And then there are transporters in that plasma membrane around it that are allowing things into the root, into the hairs, and then into the xylem, and that then moves it all over the plant. And ladies and gentlemen, this goes on for virtually all nutrients and water in the plant. Even the water is controlled through proteins called aquaporins. So water doesn't even move freely in the plant the majority of the time. And this is all done through the genes in the plant. Next one. So we won't get into how the plant does that. It's kind of complex, and I do it in a lot of my presentations because it's really cool. You just have to know that these transporters, and there's different transporters for zinc and for molybdenum and for nitrogen, are always working there and monitoring the level of the various nutrients in the plant so that the plant can adjust it. Now, if you take a look at this one, this just shows you sulfur, and the bottom part of that square, you can see at the bottom it says sulfur SO4, sulfate. And you can see that the sulfate enters the root, which is the bottom part of it, through that transporter, those little ports, those transporters. And this is sort of just confirming what it shows. So the sulfate moves up and into the vacuole, and it's stored there. Or some of it is moved up into the leaves and into the chloroplast, where it is converted into glutathione. Dan, can you get your cursor on that?
Mm-hmm.
Okay,
Where do you want me to
start at the bottom? Start at the bottom, SO4. Sulfate, right? Yeah, right here, right there. Okay. You can see that that's outside. So this is the root down here. So it moves in, the sulfate. The plant picks up sulfur, sulfate. Some of it is stored in the vacuole. Up here on the right, you can see that big vacuole. The other line goes up into the leaf on the left side, that arrow going up. There. So the rest of it goes up, all the way up into the chloroplast, right at the top. Okay? And there it is converted to cysteine. And then if you look at the right side there, looking down, here you see that word glutathione. There, see? So that glutathione now is the breakdown, or the second metabolite. That glutathione is now circulating in the plant. It's in all the leaves, in all the cells. It's moving around, and the plant measures that to determine whether it's got sulfur or it doesn't have enough sulfur. And based on what it receives, it then will do something. Next slide.
Why is the glutathione going down here again? Is it going down to the root cell again, or where's that going?
There you go. Good man. If you take a look on the left side, that's yeah, you're helping. I just know this stuff, so I don't. If you take a look on that left side, you can see those arrows going up. So what is that pipe called? That pipe between the root and the leaf?
The xylem.
That's xylem. So the xylem is going up. Goes up to the leaf to feed the leaf. The leaf then makes the glutathione, makes all the sugars, and it goes into the phloem, which is the blue pipe on the right.
Hmm.
So it's now going to take and it's going to move the glutathione back down into the roots to signal to the roots that, hey, we got lots of glutathione, or hey, we don't have glutathione. Because remember, this plant has got to get that sulfur through the root zone. I mean, plants can take in sulfur dioxide through the air, but the levels are low. So it signals back to the root in the phloem that, holy smokes, I'm short of it. So I'm going to put more of these little transporters in the root. I'm going to build them so I can access more sulfur. Does that makes sense? Hey, the plant has to have some way to know what nutrients it's short of and which ones it has lots of, because if it's got lots of it, it doesn't have to spend a lot of energy to get more of it. It's stored in the vacuole, it's stored in the leaves, stored in the stem. When sulfur is really short, you say you got an area in your field that is deficient, those plants in that area have to spend a lot of energy to try and get enough sulfur to balance the nitrogen to grow the cells. And
I feel like my mind is really expanding, Mike.
Is it opening? It's a very, very, it's complex and yet simple. If you think about it, it's like Fiddle Nelson says, think like a plant. If the plant is short, it has to do something. The plant just doesn't give up. It tries, and I'll show you in just a second how it does. When it has lots of it, it doesn't need to get a whole bunch of it because it already knows it's got an adequate supply. And that vacuole is key to storing it, because say if we're putting on a foliar feed of anything, just for general information, this plant is suddenly getting a burst of whatever it's getting into the cells all over the plant and the leaves and the stems. It can't use it all at once. So when it's moved into the cell, that vacuole becomes the key ingredient, organelle to store it. So, everybody hears about this hidden hunger concept. Well, as long as the vacuole has got the supply, the plant is adequately, resourced for that nutrient. As the plant uses it, and the vacuole shrinks, and the vacuole shrinks, and the vacuole shrinks, eventually the cells run out of those nutrients, and then suddenly we got a deficiency. Well, that process of shrinking and shrinking is, hidden hunger, and then all of a sudden it's there. So you see this response all of a sudden. That's the beauty of biosul, in my view. There is never a time where the roots aren't exposed to it because sulfate is mobile in the rooting zone. So it moves with water, with the nitrogen, which is also mobile, and is key to the cell building. So the two work in harmony, and the sulfate, if we could do that with nitrogen, and we could do that with all our nutrients so that it would move into the rooting zone and not too far so it goes totally out of the rooting zone, we would allow roots to then pick up nutrients all the time, even under dry conditions, because the roots will go down. But this is key to understanding how all nutrients work in the plant. Next one, it'll confirm this. Here's a little bit of an expansion of that. And you can see on the left is how phosphorus is taken in. See there, that's PI phosphorus, potassium. But look at sulfur on the right, the orange. Same old thing. You see SO4, and then you see the sulfur 1 and sulfur 2. Those are the transporter names that transport the sulfate into the plant. It's converted to sulfite. Now, follow that line down. It's the third dot down inside the sulfite to find the sulfide before it is incorporated into the plant. Nitrogen and sulfur are the only two nutrients that are reduced, but then it goes to cysteine, which is a major sulfate product produced, and then look what you get. Glutathione, there's that magic word, glutathione, and proteins. The proteins are incorporated in cells. The glutathione biosynthesis occurs, and as I said before, that molecule moves around the plant, and it's used to build all the sulfur-containing molecules in the plant, and also that's what the plant measures to determine whether it's got enough sulfur. Just that easy. And that works for potassium, phosphorus. All of these nutrients are handled in a similar way, but sulfur has to be reduced from sulfate to sulfide in order to be incorporated, like nitrogen has to be reduced from nitrate to ammonium before it is incorporated into the cells. Next one. We're almost done. So here's the root. This is one of my roots. This is the wheat root. And you can see, you got your cursor there? Get that
Yep.
one? Oh, there it is. Okay. So you can see the root tip, the meristematic zone here, right at the bottom, right there. That is going through the ground, and the tip is not covered. It's covered with a slime to allow it to go through, called mucilage. And that root tip is what is really involved in the sensing of all these nutrients. It's involved in measuring the pressure that is faced by the root tip, and it's exuding all kinds of exudates as it goes through the rootings, as the root tip moves through the ground, and it sloughs off that root cap as it goes and rebuilds it. And then those exudates help microbes that live in that rhizosphere zone, the little tiny zone around the root hairs. As the root grows through the root, you can notice that the root hairs start back of the tip, right? You can see the root hairs start back of the tip. And that's because if they started before that, the tip is moving through the ground, it would rip off the root hairs. So the root hairs extract most of the nutrients from the soil. The root tip is putting out exudates, and the root hairs are extracting it, and about 65-70% of all the nutrient uptake is through the root hairs in the plant. And it's that root tip and those root hairs, or the base, that epidermis, that have all those transporters that are extracting nutrients from the rhizosphere. And I'll give you the next picture. I hope it's the right sequence. No, it isn't. If that's okay, you can see this is again. Oh, go back. It's okay. It'll come. You see it? Here we are at that plasma membrane, those two rows of blue dots. So this just exemplifies, and you can see all these ports through that plasma membrane, which I showed you. And then at the bottom on the left, you see A hats and B lats. What that stands for is hats are high affinity transport systems and low affinity transport systems on the right. So in fact, when a plant is in the soil, the root is in the soil and it's measuring everything, if there's a lot of sulfur, for example, it uses what are called low affinity transport systems. In other words, it uses a low energy protein stuck in the root to extract it because there's lots of it and it's easy to get. When the plant is in a deficiency period, it changes what proteins it puts into the root hair and the root tip, and it's called HAT, high affinity transport systems. In other words, it uses other strategies that are more efficient, but those take a lot more energy. You can see it's using ATP and ADP to get, this is phosphorus. So the plant can regulate that genetically. Next one. We're almost done, folks. Don't give up on me yet. So here's a root. Here's a root. Because this is gonna make whoever's on this call is gonna make you, without a doubt, a mere 0.0001% of all farmers and biologists, other than maybe the plant physiologists, that actually even know this goes on in the plant. So you take a look at this diagram, you can see the root hair, and the one point that's important, the root hair is a single cell. You can see that it's just one cell, and it expands out here. So nutrients come into the plant, and let's take a look at what's called the apoplastic route. Just follow it. It goes in between the cells. Keeps going. It's all that blue line goes in between the cells till it hits that a line there called the Casparian strip. You can see at the top. There's this Casparian strip at the top of the diagram. And it can't penetrate that. The plant controls everything going into the root, into the xylem. Then it has to enter the cell through these little ports called, well, we don't have to worry about the plasma, it doesn't matter. And then into the xylem and up it goes. The symplastic route, the red line route, which, I'll have to do this at another one where guys can see. That's all that one. You see, right away it goes into this, and stop right there. You got little transporter you just went through? That immediately allows it to go right into the cell instead of in between the cells, and then it goes from cell to cell to cell and into the xylem. So the plant is controlling everything in the vacuole, in every cell, what enters the plant, what leaves the plant. If a plant has too much of something that's toxic, it will actually force it out of the plant, which is called efflux, and it's forcing it out of the plant to get rid of it because it's poisonous, which makes a heck of a lot of common sense. Next. And here we go. This is the internal workings of the cell. And I won't go into in detail, but you can see that blue lining all the way around it. Up in the upper left, you see the nucleus, which contains all of the genetic material, or most of it, because the mitochondria. So within each cell, and it's got this sort of system of canals running all through it. You can see all those lines running through it. And then if you pull your cursor down to the bottom of that cell, right down there, keep going down, you should notice that, wow, this cell actually has access through that channel to the next cell. What we now know is that all the cells are connected to each other through these ports called plasmodesmata, and that system of rivers that runs in the cell that you see there runs from cell to cell to cell. That's called the endoplasmic reticulum. So the cells can actually link to each other and do work together. When a disease attacks, all those cells can shut down, called systemic acquired resistance, and they can move nutrients from cell to cell. And we're just now learning they also can move RNA from cell to cell. Next one. And this is, I think, the second last one. Now, here's the thing that sulfur has going for it. Really big. It's a simple diagram, and yet it's so important. If you look at the right root, you have this basically depicts you got water going in along with nutrients everywhere at the root tips and moving up and up and up. And you can see as it moves away from the root hairs, there's nothing coming in. If you look at the left one, you can see that this is depicting that water's coming in all the way up past the root hairs and root tips. And that can't happen because the plant is taking water up through transpiration. If the plant could take up water through transpiration through all the old parts of the root, it would have a massive amount of open cells that would have to be sucking in the soil. And the plant cannot transpire that much nutrient or water out to do that. So it shuts down after the root tips and further back to the root tips. It sclerotinizes the roots. So it keeps the majority of the pull near the root tips where the root hairs are. That's why, as we get drought and the roots go down, the plant takes up water as it goes further down, and it sclerotinizes everything back of it so that it doesn't lose the water on the way up to the shoot. That's the problem with the immobile nutrients that are near the surface. As the roots move through that and deeper into the soil zone, the rooting zone, it loses its ability to pull those nutrients near the surface because now it's pulling water from deeper in there and it's sclerotinized all that. When you and that's the beauty about the sulfur and the nitrate. And a lot of people think they got that big crop last year because the roots went down and pulled that lost nitrate from deep in the rooting zone to give you high protein and give you the crop you got this coming year. With sulfate, because it is mobile, it's going to move down into that rooting zone over time, not immediately, but over time, and it's going to be available through those root hair tips. Now, the trick is when it rains again, it re-stimulates those upper roots, and you get some new growth and uptake one more time. So the plant re-stimulates those plants closer to the surface, and that's how it gets those phosphorus and potassium throughout the growing season, because the roots are usually a lot deeper. Most of the roots in a plant are in the top foot, but in a drought condition, they'll go down 3-4 meters if they have to, but that costs the plant a lot of energy. Last one, I think. Last slide.
I don't know that there's another slide, Mike.
Oh, okay. I see one on my screen. That's the only reason I asked. No, that's you. So anyhow, ladies and gentlemen, that's it. And I hope, I always struggle with this because it's a pretty complex situation that nobody's probably even addressed for you before. But the key end product is that these plants have mechanisms to extract all nutrients and water. The trick is that when the root is doing all of this, it has to be fed by the shoot because the root has no ability to feed itself. So that's what's called a source and sink kind of situation, where the leaves are the source and the roots and the fruit and everything are the sink for the nutrients, because the shoots produce all the sugars and do all the metabolic processes to make all the elements in the plant. Knowing that and knowing that sulfur is key to stress management and key to production of a whole bunch of things, and proteins and lipids and vitamins in the plant, puts biosul in, to me, a strategic position to supply the plant with something it needs that is extremely variable in the soil and is reducing in the atmosphere, which used to supply all the sulfur for our plants. So I see nowhere, and this is just my own digging into this, I see nowhere but up for the use of biosul and sulfur moving forward. That's the end of my spiel.
Hallelujah. Hallelujah.
Hallelujah. And like I said, for you guys that don't know me, I came to these conclusions totally independent once I found out about sulfur, because I hadn't really looked into it other than, else than saying we need it and we're running out of it. But this is why we need it. And I'm hoping that gives you the confidence to go out to your clients and say, you know what? This thing is something you absolutely need. No ifs, ands, or buts. Under all circumstances, your plants will need sulfur. And we can't measure it in the soil because it's so variable. So you know what? Put some on. Put a quarter on. Put a half on, whatever. But try some. I think if you can get them to try it, you'll have them sold in no time flat.
Awesome.
I'm not even a salesman.
Oh, this drives me nuts about people because, frankly, you did a great job of selling something very naturally that you're passionate about and believe in at the beginning, and that's absolutely what it's all about. And I refute that claim by so many people in this life, and I don't know what it is. I mean, if maybe you think sales is something akin to being a used car salesperson, but I can tell you, everything that we that predicates our modern life has been sold by somebody in good faith. And Mike, you sold yourself to Agritrend, to the customers that believe in you, to your spouse, you sold me on coming to the clinic. You said, "Dan, I will not disappoint. I always deliver," and you did. So you're a hell of a salesperson. Let's just admit it here. Let's be real.
And I just would make one comment. This, for guys that are listening, if this sort of went over your head, it's something you can't kind of absorb in one session. So over the next few years, we'll probably ramp this up, and if you come to things like farm form events, you can get another shot at this, because it's this understanding of the cells that is really going to be the key to agriculture in the future. The broad scale part of it, we're going to put down NPKs and micros, and we're going to seed, and we're going to have better varieties will happen by itself. It's the understanding of the cells that is allowing scientists on a global basis now, because of their understanding, to take a lot of these traits and these proteins that are transported, and they're going to make plants that are going to be saline tolerant, pH tolerant, to the best of their abilities, and that's going to really be the secret for hopefully feeding all these people that are going to come around in the future. So don't, if it seemed overwhelming, I'm hoping that just the principle that this plant knows what it's doing is going to give you confidence. Okay.
Hey, Mike, Dan.
Yeah.
Elston,
go ahead,
Elston here. Yeah, I just want to say thanks, Mike, for that very good presentation. A little bit complex in places, but bang on the money. And something popped into my head. So for the people that are still on the call, the way I think of vacuoles and cells is kind of like a gas tank. And that gas tank holds a lot of different nutrients. It helps the plant deal with a lot of different things. And one of the things that we've learned a long, long time ago is the most important ratio in a tissue test, no matter what the crop is, the most important ratio is the N/S ratio. And for those of you that have been taking tissue tests, often your tissues are coming back high in the range or well above the range, and that's because the plant is storing sulfur, excess sulfur, well, not really excess sulfur, but sulfur in the vacuoles, and that sulfur that's being stored in the vacuoles can now be turned into stress fighters that Mike related to, glutathione, what's the other one that starts with P, Mike?
The phytoalexins.
Phytoalexins, and there's a whole bunch of research coming out right now that shows that that elemental sulfur in a plant is like almost like a antibiotic inside of a plant. And so a lot of cool stuff here, Mike. I connected a few dots here this morning. I'm glad I woke you up, and yeah, good job.
Well, I showed that, why I showed that vacuole, and you're right. The sulfate, it stores the sulfur as sulfate because that's the original intake product. And that's why in the end, we'll have to have this conversation, because there's a lot of thinking that the plant can't move sulfur. But whatever's in the vacuole that's stored as sulfate can be remobilized, apparently, which makes sense because it hasn't been converted to anything. And as this vacuole shrinks down, it can give it to the leaves and move it out of the leaves through the phloem to other parts of the plant. But the other part of that, if you can recall, that vacuole had transporters for all the nutrients. So if it's a little bit short of K, and there's K in the vacuole, let some K out into the cytoplasm to be used. If it's short of molybdenum or whatever, it has all those transporters in that vacuole envelope. So it's regulating all of these nutrients at the same time in response to what's going on in growth and stress. It's a miracle that just amazes me that these plants can do that, and they have the genes, many more genes than a human being, in order to do all of these things.
Yeah, so it's like, sorry, if we start thinking about the plant as its own nutrient storage system, and as long as the nutrients are stored in the vacuole so that they're not fixed, then they are mobile, and that all makes sense to me. So, yeah, that's pretty cool. Connected a few dots this morning. Thanks, Mike.
You bet. I hope that
Mike,
helps, Dan.
For producers that are concerned about high protein levels in malt barley and too much sulfur in the mix, what would you say to them?
Well, I'll say Elston should talk to you, but that's a problem of the ratios are out of whack.
Right.
Elston's the expert on this, but my understanding, the ratios are just out of whack. Elston,
yeah, the whole concept of not using sulfur on malt barley because of protein is idiotic, to be blunt. And the reason it's idiotic is Mike had a slide there that showed the variability of sulfur across a field. So if you're not satisfying the plant's requirement for sulfur in the 20 or 30% of the field that's deficient, the way the plant responds to a lack of sulfur is it reduces, the yield becomes reduced. And when the yield's reduced, what happens to the excess nitrogen? It gets concentrated as protein. So if you've got enough sulfur across the field, across that variable sulfur field, and the plant in the sulfur deficient area can access adequate sulfur to maximize its yield potential, what happens to the nitrogen? Well, it forms protein, but it only forms the amount of protein that's governed by the yield. So if you've got deficient areas, you reduce yield, you concentrate nitrogen as protein, you get high protein. If you dilute that nitrogen across yield, you get low protein. It's as simple as that.
And it's affecting your yields in your pocketbook in the end.
Jerry had his best malt barley ever, I think, this year, and he's pretty much done his farm with biosul there. So,
well, and that's the whole thing. You got to think about balanced nutrition. You got to think like a plant. You got to realize that a plant is growing in an ocean of four-dimensional nutrient variability. So, Mike could go off on some of that four-dimensional stuff, and he sort of did. But if you're looking after the balance of nitrogen and sulfur in a plant, as well as the other nutrients, in this case a malt barley plant, the whole thing is optimizing yield across that variable field, sulfur being one of the key nutrients to get you to your optimal yield, and not allowing the plant to concentrate nitrogen as protein in areas that are yield limiting. It's just that simple. And there's days where I wonder if we're actually in the 21st century, because this stuff has been known for like decades, man, decades.
Anyway, and Andrew Clement said the same thing to me last week in Calgary. He says, barley, we got massive yields and our protein was fine. And he says, that he believes it was the sulfur that was doing it. Exactly what Elson said. Big yields and the protein was just fine.
Perfect. One last question, Mike. If you could, if you had like 1 minute to tell your 20-year-old self something, what would you say to your 20-year-old self?
To my 20-year-old self, I'd say I'd be in the sulfur business if I was in the farming business. I'll tell you that much. And I'll tell you the other thing is coming. There's going to be for spreaders, and I'm assuming all these guys are spreaders. There are going to be other opportunities coming up at spreaders, and you'll see some of that this year at Farm Form event, because the days of calcium are coming closer and closer to us being able to spread limestone in this province. And I think you guys that are set up.
Go ahead.
Go ahead. And I think the guys that are set up to be spreading this, and if it's a pelletized calcium, will be in the business somewhere down the road where we got acid soils and spreading calcium.
Well, I spent the day traveling from Regina to Landsberg with Neil Wiens, the inventor of the product. Mm-hmm. And I know that he's working closely with Elston on a lot of different things, but there's a lot of things I can't tell you.
Right.
But I can tell you that there is a lot of interesting potential things coming down the pipeline to enhance your investment and your hard work in not only equipment, but in your customer base. So I'm going to wrap it up at that.